Right, let's try to finish this chapter number 2 of our class. Remember that if you need French version, you can find a link in the comment. So the chapter number 2 is about origin of soil and grain size. So in the previous 2 videos, we have talked about all these points from number 1 to number 7. In this video, we will try to talk about number 8 and number 9. Number 8 is about particle size distribution curve. And the last point, number 9, is the shape of the particle of the soil. Okay, so let's start with the number 8, which is particle size distribution curve. We will try to find what information this curve can give us. So this particle size distribution curve can provide a lot of information about the soil, as I told you in the previous video. So if we take, for example, this curve, particle size distribution curve, we know the name now. From the previous video, we know the name. And what can we get from this curve is, number 1, effective size. The effective size means the effective diameter of the soil. So that means if we see here, this curve, 10%, it means that diameter corresponding to 10% finer on this curve, particle size distribution curve. It means that this diameter, if we take, for example, here, in our case, it's 0 point something, a little bit higher than 0.1. So it means 10% of the soil means the mass of our soil, our sample, have diameter smaller than this diameter. If we consider that this is 0.0, I don't know, 12, for example, it means that in millimeter, don't forget, it means that 10% in gram, the weight of the soil sample has diameter particle smaller than this diameter. The particle of that part smaller than this diameter. That's what it means, 10%. Okay, so what else can we get? From this effective size is used for estimation of hydraulic conductivity of the soil. What is the drainage capacity of the soil, actually, the granular soil especially. So it's very important. Number 2 of what we can get from this curve is uniformity coefficient, CU, like this. What is this coefficient? Uniformity coefficient is, we just take D60 and D10. You know D10. So D60 is just same as D10, but this time 60% of the particle. See, 60% finer. So if it means that if you take this, for example, let's say this 60 is 0.5. So it means 60% of the particle of the soil have a diameter, grain size smaller than 0.5. And how can you get this diameter, D60? It's very simple. You see here, this y-axis is about the percentage. So you come on this axis and try to find 60%. 100% is the max. 60%, and you make a projection on the curve and if you go down, you will get the corresponding diameter. So in this curve, it means that D60 is corresponding to about 0.5 millimeter, which means that 60% of our soil sample has diameter smaller than 0.5 millimeter. Okay, so you can try for also D30, 30%, you go on the curve and you go down. D25, say 25% on the y-axis, and you project on the curve, and you can get your D25. So this uniformity coefficient is just a ratio of D60 to D10. Means D60 divided by D10. It will give you the uniformity coefficient. So this is telling us if the soil is uniform or not, something like that. By soil, I mean the size in the soil, the particle size. So it indicates the uniformity, or again, range of particle size. Okay. So this is the second information we can get from this curve. Number 3 now, we can get also coefficient of gradation. Coefficient of gradation is just gradation means if the curve is very well graded or bad graded, something like that. We will talk about this later. But if the curve is just long or it going vertical, something like that. How vertical is this curve? So this coefficient is telling us that. So how to get this coefficient? This coefficient is obtained from D60, D10, and D30 by this equation. This coefficient, you take D30 square and divide it by this product, D60 multiplied by D10. It will give you this coefficient. So remember, this coefficient is telling us about gradation of the soil. Number 4, sorting coefficient given by this formula, D75 divided by D25, and we take square root of this. This coefficient is actually another measure of uniformity of the soil, but it used mainly by geologists. Yeah, we don't use this too much in geotechnical engineering. Actually, I've never used this. Okay, what else can we get from this curve? We can get a lot of information. So we can get also from this curve the percentage of gravel, sand, silt, and clay size particle. Do you remember that we don't say clay? We say clay size particle because those particles, they might have size, same size as clay particle, but they might not be clay mineral. And we have seen here what difference clay mineral can make. Very big difference. Okay, so from this curve also we can get the percentage of gravel, percentage of sand and silt, percentage of clay size particle. How can we do that? Very simple. If we take example this curve, we have seen this curve in the previous video. If we take, for example, this curve, we can, from this curve, we can try to know percentage of sand, gravel, silt, and clay size particle just from this curve. This is another information the curve can give us. Okay, now remember, we will try to do it by using this unified soil classification system. Do you remember in the, I think, the previous video or the first video, I don't remember exactly, we have seen different method of classification of soil that include unified soil classification system. Okay, so we want to use that system to find percentage of gravel, sand, and silt in this soil sample. Okay, just as a reminder, I will put this table here. We have classification MIT, a lot of classification, but the one we will be using is this one, Unified Soil Classification System. Okay, so this system is telling you that in size, don't forget it in millimeter, from 76.2 to 4.75 in millimeter, it gravel. And from 4.75 to 0.075, it's sand. And the system doesn't give any difference between silt and clay, okay? Just after 0.075, we consider this as fines. So we are going to use this system to find the percentage of gravel, sand, and fines in the previous curve using. Okay, so don't just remember this. So this is the curve. So we will try to remember the range of the sizes and try to calculate the percentage. Okay, this is, for example, let's try to find diameter 76.2. What are the percentage of the soil going through smaller than this size? If we see the largest size of this soil particle is even less than 5 millimeter. So we can say that 100% of the soil is smaller than this size, 76.2. That's right. Okay. How about 4.75? You come here, and this is 2. So maybe 4 is around here. I think the biggest size of this soil is about here, just a little bit higher than 2. Okay, so I think it also 100%. That means all this grain size on the particle of this soil are smaller than 4.75. So we put 100% also for this. How about the diameter 0. This one, 0.075? Okay, that one, we can say that it around 62%. Yeah, 62%, because this is 0.05 and 0.1. Just don't forget that this is logarithmic scale. Okay, yeah, don't forget that. So it is not in the middle of 0.1 and 0.05. So based on this, we can say that it is like 62% of the soil, yeah, smaller than diameter. Yeah, all this part is smaller than 0.075. Okay, so remember that this unified classification system is just limited to here. All the rest, maybe we can put like 0 here. Of course, we cannot put 0, but remember that everything smaller than this, then is the rest. So 0 is just 0%. Okay, then from this, how can we obtain the percentage of gravel, sand, and fines? So gravel is between this and this. Since gravel is between this size and this size. We're gonna do this minus this. 100 minus 100. It will give us this. It means 0% of this soil is gravel. No gravel in this soil. And then for sand, remember it's between this size and this size, it is sand. So we will do this one minus this one. 100 minus 62. It will give us 38%. So it means 38% of the soil is sand. Sand. And the rest will be, of course, defined. It means silt and clay. 62 minus 0, it will be 62. So we can also obtain the amount of gravel, sand, and silt and clay in the soil just by using this particle size distribution curve. Okay, very important. Okay, let's continue. What else can we get from this curve? We can get the coefficient, uniformity, and coefficient of gradation. We can get the percentage of each type of soil, gravel, sand, and fines. But we also can get from this curve not only the range of particles, but also it tells us the distribution patterns. Pattern means like different type, how the soil is distributed. Is it like various soil particle or very uniform? We will use this figure which show three curves. Okay, three curves. These curves are different. We have curve number 1, this one. Number 2 is this one, and curve number 3. Okay, let's start with the curve number 1. What this curve tells us, this curve is typical curve we call poorly gradated soil. It means that the majority of the soil grain are almost same size. And you see that this curve is almost like is tending to be vertical. Okay, it's not inclined like this. It's going to be vertical. It doesn't matter if it is here or here or here. It just almost vertical. It means that in this soil, all the grain have almost same size. That's the meaning. So we call it poorly gradated soil. So poorly graded soil. Okay, not gradated. Poorly graded soil. It's like grade 1, grade 2. Okay, poorly graded soil. And this soil lack of wide range of particle size. For example, if you take all this range of soil of diameter is not included in this soil, and also all this range of soil is not included in this soil. That's the curve number 1. Curve number 2 now. Oh, this one, the middle one. As you can see, this one is covering a large, very wide range of diameter. Okay, so we call this well-graded soil. So the particle size are distributed across wide range, wider than the previous one. As you can see, the previous one stopped here. and this one is going up to here. And from here is the bottom one also. The previous one, number one, is stopping here, while this one is going up to here. So it's covering a wide range of particle size. Okay, so we call this type of curve well-graded soil. So this well-graded soil have uniformity coefficient greater than approximately 4 for clay and 6 for sand. So this means that if you are dealing with gravel, this, and you have the uniformity coefficient greater than 4, your gravel is well graded. And if you are dealing with sand, and that sand has coefficient of uniformity coefficient greater than 6 here, then your sand is a well-graded sand. That is very important, please remember. Okay, so if we have seen just now how we can obtain the type of soil using this curve: gravel, sand, and fine, using the unified classification system. So if you have determined that your soil is in majority sand, for example, and you have found that the uniformity coefficient of your soil is a little bit higher than 6, then your sand is well graded. Okay, remember that. But if it is gravel, so mean the diameter of the soil fall at least the good percentage of the soil fall between the size of the gravel. In that case, if you have a soil like this and the uniformity coefficient is around 4, then maybe a little bit higher than 4, then you can tell that your soil is well-graded gravel. Okay. Okay, let's move to the curve number. Okay, just a reminder, this formula is formula for this uniformity coefficient. Okay, you know already. And another thing is, if the coefficient of gradation, which is this one, so this is coefficient of gradation. For well-graded soil, typically falls between 1 and 2 for gravel and sand. That means you can combine these two based on the coefficient of uniformity coefficient, and this coefficient of gradation. You can combine the two and tell if your sand or your gravel is well graded. So for this uniformity coefficient, we have already talked about 4 for gravel and 6 for sand. But don't forget this one also, coefficient of gradation should be between 1 and 3. It means that for sand, if you have determined that your soil have particle size that fall in between the size of sand according to the classification you are using, and you find out that the uniformity coefficient is around 6 for sand, and the gradation coefficient of gradation is between 1 to 3, then this sand is well-graded soil, well-graded sand. And for gravel, this uniformity coefficient around 4, greater than 4, and the gradation coefficient between 1 and 3. The two conditions, don't forget. In that case, it means that this gravel is also well-graded gravel. Okay, please let's go to curve number 3 now. As you can see, this curve is a little bit strange. Here, this one, sorry, this one. Number 3 is a little bit strange curve. This type of curve represent gap graded soil. It means that the soil with combination of two or more uniformity graded fraction. So this part is like one part which is uniformly graded, and that part, the second part, this one, is another part that is uniformity graded, and there is like somehow of link junction between the two. So it means that this gap graded soil have gaps or missing particle size. Some particle size are missing between them. Maybe around here, some particle size are missing. So you have just you have to join them like this. So in that case, I mean, if you do the sieve analysis, the middle sieve somehow will not retain anything at all. Everything will pass. So you will have the upper sieves with soil and the bottom sieves with soil. The middle one are empty, nothing there. So in that case, but you still have to join the two portions of the curve. For example, here you have to join. We sometimes have also this kind of curve. Okay, let's try this one exercise. So here the exercise is giving us the sieve number. You remember the sieves have number. So it's not any time we have to use all of the sieves. Okay, here they have used only this, but this one is very important. They receive 200. It's very important because it's the soil that will go through this one. We will take to do the hydrometer analysis. Okay. Yeah. So here this exercise doesn't give us the opening sizes, the diameter of the grain, only the sieve number. So it means you have to go back to this the table of the sieves number and find out which number correspond to which size, which opening size. And we see here the mass of soil retained on each sieve in grams. That one is okay. So we are asked to perform the necessary calculation and plot the grain size distribution curve. Secondly, we have to determine D10, D30, D60 from the curve. Number 3, uniformity coefficient. Number 4, coefficient of gradation. Just as a reminder, I give you here how to calculate the two coefficients, uniformity and gradation. Okay, so I just remind this one also. Okay, how we step by step how we obtain the fine percentage. Okay, so after shaking your soil sample, you will obtain on each sieve a certain amount of soil, which has a certain weight, mass. So after waiting, we have to wait means to obtain the mass of retained on each sieve. This is a reminder. We have talked about this in the previous video. Okay. So step number two, weight the total mass after drying, and by additioning all the soil retained on the sieves, we can get the total mass. And number three, then we can calculate cumulative mass on each sieve, which means additioning the total mass retained above that corresponding sieve. And the passing mass is just total mass minus the cumulative retained mass of each sieve. And after that, we can calculate the percentage of each sieve. Percentage of passing means percent final by using this formula. So the mass passing divided by the total mass, and you multiply by 100 to obtain this in percentage. Okay, just a reminder again, here are the number of the sieve number and the opening, because the exercise didn't give us the opening size. But you remember that for us to make this graph, this curve, we need the size, the diameter size, which will be in x-axis and which should be in logarithmic scale. Okay, so we have to make a correspondence between the sieves number and the opening. Yeah, because we have to use this opening in our analysis. And remember that anytime you do this sieve analysis, please include this one, the number 200. That one is very important, because it is after that one, you can just put the pan, and then the soil going through this one will be used for hydrometric analysis, hydrometer analysis. Okay. Then after this reminder, let's go now for our exercise. First, the calculation to obtain this curve, the plot. We do first the correspondence between the sieve number and the opening, as I explained before. So sieve number 4, the opening is 4.75. Number 10, 2, and so on. And then the exercise has given us the mass retained on each sieve, that is here. So we don't need to do anything. So now we can calculate cumulative mass retained above each sieve. So that is simple. If you are here, for example, it's 0, of course. And if you are here, you do this one plus this to obtain this. Okay. And this one plus this to obtain this. This one plus this, you get this. This plus this, you get this. This is the formula here explained here. Okay. And then after this, at the end, you will get the total mass of your soil sample. Then you can get the percentage. The percent final is just the passing. How to obtain the passing? Total minus cumulative. Okay. total mass, which is 450, minus cumulative. This is how you obtain the passing. And then you divide this by the total mass again and multiply by 100 to obtain the percentage. This is the percentage. So if you do total for this sieve, for example, sieve number 4, means this opening, your total, which is 450 minus 0, it will remain 450. And divided by 450 means 1. Multiply by 100. So you get 100. For this one, sieve number 10, opening 2 millimeter, the total 450 minus 21.6, okay, and you divide by 450, this result multiplied by 100, you will get this. So now, by using this, of course, you will do all this column, you will do to obtain this. By using this and the total mass, you can obtain this column, the total. And then we use this percent final. How the percent final and the opening, we use them to draw the curve like this. So we know that this 0, 100, opening 4.75, it's 100%. Donc 100. Don't forget that this here should be log scale. That is very important. Only this one is log scale. Next, the opening 2 millimeter. So 3 is here. 2 millimeter around here is corresponding to 95.2. So 95.2 is around here. Okay. Next point, the 0.85. 0.85. That one is 84.2%. Okay. So 1 is here. 0.3 is here. So I guess 0.85 is corresponding to this point. And you know that the percentage is 84, a little bit higher than 80, 84 point something, 0.2. Okay. Then you do that to obtain all these points. And by joining the point, you will obtain your curve. That's very simple. That is the first question. Second question is D10, D50, D30, and D60. So you know this D10, you go 10%, 10% is here, 10, because this is 0, 20, 40, 60, 80. So 10 here, you do projection on the curve, and then you go back in the x-axis. Yeah, so it will give you the D10, which is here 0.41 millimeter. Okay, and D30, 30%, 20 is here, 40 is here, so it will be just in the middle, because this one is not logarithmic scale, not log scale, so it will be exactly in the middle. So you go on the curve and go down here, you will get 0.185 millimeter. That your D30. D60, same. Here and here, you get 0.09 millimeter. That's it. Question number 3. So I will just put these here because we will use them again. So uniformity coefficient. Do you remember the formula? You use D60 and D10. D60 divided by D10. So D 0.41 divided by 0.09, and you will obtain something like this. And then the coefficient of gradation. That one is obtained by this formula. So it gives us 0.93. Yeah. So I think that's all for this eighth part of this chapter. So all about the particle size distribution curve. I hope you have learned something about this. Everything, all information we can obtain from the particle size distribution curve, you know now. So let's move to the shape of particle. This part actually is really neglected in the geotechnical engineering. So the particles size shape also play a really crucial role in the physical property of soil, but people neglect it very often because there are a lot of challenges associated to this. How to measure, how to know the shapes. Sometimes we even need microscopes to know the shapes of the particle, soil particle. Okay. But okay, there are three major types of the particle shape we have: bulky one, flaky, and needle shaped one. So this bulky particle one, the most maybe in sand, you have this one, mainly formed by chemical and mechanical weathering of rock and sand and mineral. So geologists are using terms like angular, subangular, or subrounded or rounded particle. So just here, angular, subangular, subrounded, and rounded. This is geologists are using this mainly. So the shape of granular particle in soil mass, they greatly affect a physical property of soil, as we stated before. So what physical property of soil it can affect? The void ratio. Don't worry, we will talk about this later. What is void ratio? The shear strength. We will talk about this also. A compressibility of the soil. So these three physical parameters of soil are greatly affected by the shape of the soil particle. Okay, and the shape are changing when the sand or like gravel, the soil is transported from one point to another, like long distance by wind or water. So understanding this particle shape is very important for evaluating the engineering behavior of soil. Okay, we still talk about this bulky soil particle. We can calculate what we are calling angularity of this bulky soil particle, which is defined by average radius of corner and edges divided by the radius of the maximum inscribed sphere. Okay, another parameter we can calculate is sphericity of the particle, which is S equal dE divided by LP. dE is equivalent diameter of the particle, which is obtained by this one, this formula. In this formula, V is the volume of the particle in pi, okay? And LP here is the length of particle. So by using these two, we can obtain how spheric the particle is. And this one, A, how angular the particle is. Let's talk now about the flaky particle. This photo, microscopic maybe, shows these are bulky particle, but this one is a flaky particle. It shows the difference. The difference is very important here. As you can see, these shapes affect the physical property of soil. These particles, they have very long sphericity. They have very long sphericity, usually around 0.01 or less. So these particles are mainly clay mineral, mainly. And the last one, last type, needle-shaped particle, shown in this photo, this figure. As you can see, it's just like needle. And they are much less common than the two other types. Example of soil containing this needle-shaped particle are some like coral deposit and anthracite clay. So I think about shape also, that's all. So that is the end of this chapter, chapter number 2. So thank you very much and see you for the next chapter, chapter number 3. Thank you very much for your time.